Good evening, all. On behalf of IEEE VTS SBC NSSC and IEEE SP NSSC, I extend a warm welcome to everyone gathered here for today's session on connected vehicles. We are privileged to have Ms. SRIPRIYA GN, ex-head of product connected platform at Aether Energy, as our distinguished speaker. In the rapidly evolving landscape of automotive technology, Ms. Sripriya's expertise is a beacon. Her role at Aether Energy has been pivotal in shaping connected platforms, and we are eager to absorb the insight she brings. This session promises to be a valuable exploration into the world of connected vehicles, and we appreciate your presence as we collectively delve into the future of automotive innovation. Without further ado, let's welcome Ms. Sripriya GN and embark on a journey of knowledge and discovery. Ma'am, the stage is all yours. Thank you.
Hi, thanks, Nandana. First of all, am I audible?
Yes, ma'am.
All right, great. Hey, so thanks for that wonderful introduction. As she said, I recently decided to take a break, and pretty much from this week, I'm on my career break. But up to last week, I was leading connected platforms product management team at Aether, and along with that, also other vehicle software and the sales and support software products at Aether. So I'm really glad to be here. So just a quick few things. It would be nice to see faces for most of the people who are online, so that it doesn't feel like I'm speaking to a screen. So whoever are able to turn up, that will be nice. Secondly, the whole point of this is of this session is I'm hoping to learn as much from you. I'm sure a lot of you are learning new concepts, the theories, and I'm sure you are doing your projects in your as part of your college assignments. So whatever questions you have, or even ideas, different points of views, anything else that you have heard elsewhere, I would love it if you actually share. So go ahead and either raise your hands, put it in chat, however, preferably if somebody wants to speak up, you can feel free to just interrupt me as well. Okay, so with that, I'll start. Just give me a moment. Okay, let me know if you're able to see my screen. I don't know if I have a response. Are you able to? Are you not able to? Am I audible?
Yes, ma'am.
Okay, are you able to see my screen, the slides?
Yes, ma'am.
All right, cool. So then I'll get started. Okay, so first things first, I'll just have some patience, but I will be slightly technical, to just bring you guys some framework in terms of how we look at connectivity. But before that, just so you all know, when we look at connected vehicles, end of the day, at least the way I perceive it is, it's a more specific domain within the larger smart devices, Internet of Things, IoT, whatever you want to call it. So, for example, when your Bluetooth headsets connect to your phone, that for me is a connected device. When your lights are like these days in our houses, we have smart lights, we have smart cookers. That's a connected device. So anything in general that you see around, and you see that it's a physical device but has some form of command and control that can be done remotely, and most often either through Bluetooth or through internet, then that would come under the larger scope of IoT or connected device. And when it comes to connected vehicles, it is simply a specific domain of a vehicle, but it is, I would see it still as like an IoT, an application of an IoT. So coming to what a connectivity stack includes. So just read this from the bottom as I'll take you guys through that. So first of all, as you see the bottommost layer here, it's a hardware layer. Basically, when I say hardware, I'm referring to electronics. So either ECUs, electronic control units, sensors, even any drivers, MCUs of any of the peripherals, all of those would fall under what you call as the hardware layer. So think of hardware layer as anything which is physical, but it has some form of an electronics device attached, as a requirement to be part of a connectivity stack. So once you have the hardware layer, the next point of decision in your stack when you're building the whole connectivity solution or a platform is to think about how do you want these devices to communicate and to whom. So when it comes to the how, the the technologies that we have in terms of the connectivity are, frankly, you either take Bluetooth Classic or these days the more popular BLE, which is Bluetooth Light Energy. We can have Wi-Fi based connectivity, or even 4G and 5G. In many cases, you would find that devices have more than one of these as part of their connectivity modules. And then while OS, which is operating system, is not a strict necessity, at least any decently large enough or powerful enough devices do have operating system also. So it can be Android, Linux, or any other operating system that's out there. But as I said, it's not a necessity. For example, your airports may not have an operating system and may be directly communicating without that. But that functionality of operating system or whatever is required is definitely built by those engineers. The next part is to figure out, or rather define, a connectivity gateway, which is, think of it as a software application that's capturing all the data from these sensors, basically the hardware layer, processing it in a way that's understandable and sending it to whichever other devices. So that's the function of a connectivity gateway. Then above that is actually the devices with which you're connecting. So in case if it's a Bluetooth headset, it's a mobile phone that's actually, it's communicating with. Most of the devices today, whether you directly see it or not, also connect to the cloud servers, even if it's for non-user facing application. So I would say that while it's, again, having a cloud connectivity is not a must have as a connectivity stack, most devices today have it. And finally, on top of it is applications, which is, end of the day, connectivity is just data exchange. But what you do with it is really the applications. So all the applications would be what we consider that sit on top of it. So that's very roughly the connectivity stack. And as the diagram that you see here, while this is what is applicable to any connected vehicle, as I said, this set of technologies is what is also applicable for any generic IoT IoT devices. So that would include, as I said, your applications in robotics. You consider drones, etc. Even say your smartwatches. These days, or a lot of these health tech wearables are coming up. All of these will have some a similar stack. So I'll pause. Any questions, comments so far? Cool. I'll move move on then. Yeah. So while end of the day, when we talk about a connectivity stack or any connected vehicle, that's technology. But what exactly are the functionalities of that entire stack of platforms? So I can divide it into four key functionalities. Correct. So the first one is what we call as the device management. This is, by the way, there for all mobile phones as well. So each of your mobile phone that you're carrying has device management as one of the core functionalities. But when it comes to even any of these IoT devices, or in this specific case, a connected vehicle, device management would include basically identity. So, for example, when a scooter gets to the end of line on a factory, it needs to have a digital identity itself. It needs to have a name that is stored in some software application, so that we know that this scooter is, say, scooter 123, and that's called and that part of the device management is called device registry and identity. And then that also assigns an identity to that scooter. And when you have an identity, what you can do is you can actually do a lot of control on access management. So you can say that uh, all devices that are, say, from 0 to 100 will have a certain kind of access. From 101 to 200 will have another kind of a functionality, and so on. End of the day, you can control a lot of things just by software if you know which device you need to talk to. And for that, it's important that you first register the device and define an identity. It's almost like like as humans, we all get our birth certificates, we all have a name. So it's important to have that similar kind of an identification for every single connected device out there, and in this case, every single connected vehicle. So that's device management. There is also authentication and security. So while the a connected scooter communicates with other devices, it's important to have a mechanism to authenticate that it's a genuine scooter, and it's not some some rogue scooter or somebody actually trying to hack into the system. So authentication and security are also important functions of device management. The second important functionality is what we call as over-the-air updates. So this is about, as you must have now heard, for example, again coming back to say smartphones. Periodically, you keep receiving updates of Android or iOS, right? Like I think iOS today is on version 14 or 15 or 16. Similarly, Android is on, say, version 10, 11, 12, and so on. So those are the updates, are basically software updates being made to your phones without you necessarily having to go into a station and saying, okay, you know what, upgrade my phone. That process is called over the air updates. So as I said, in this case, even the scooters, or in general any connected vehicle, even the cars, do get periodic software updates. So that includes being able to control the device, doing any data exchange. But the primary functionality or the output of that is that the software of that car or a scooter gets updated. The third key functionality is what we call as telemetry and data logging. So this is actually every being able to get. You can think of it as sensor data. In case of electric vehicles, it includes battery data, motor data, uh, and a lot of these actions, such as, okay, is the vehicle has the vehicle be on key on state, is it key off state, is it in parking state, and so on. So all of this is called as telemetry data. And usually this is generated the different components generate this at fairly high frequency, which is anywhere from 1 hertz to 100 hertz. So imagine 100 data items of one single data item coming 100 times in a single second. And These data items also number in the range of close to 1,000, 2,000, and so on, for a two-wheeler. And for four-wheeler, I assume it's in, obviously, you can have data parameters which are 10,000. So imagine 10,000 parameters, each of which is coming at a rate of 100 per second. That's the amount of data you have to ingest, and process, and then do the storage. And and sometimes, and also some of that processing has to be given to the user or used for any other application. That's the kind of crazy scale we are talking about when it comes to telemetry and data logging. So it's similar to the scale of, say, what a Netflix or a Twitter applications actually today handle. It's Many companies who have connected vehicles today are getting to actually handling that kind of a scale. The final functionality is command and control. And this is where several applications to control the the devices come in, which is, I'm sure if those who have been following Aether uh, would have heard of applications like, you can, if somebody makes a call, you can accept or reject a call. If you can actually detect whether a vehicle is being, say, like you actually get a theft alert on your vehicle or a tow alert if somebody is moving your vehicle. So all of these are command and control applications. Even if it's in case of cars, you can remotely you can remotely um, oh, open the car or close the car. You can open the trunk, close the trunk. You can turn on the AC even remotely. All of these are called command and control applications. So that would be the overall, I would say, categories of functionalities of a connected platform. Any questions here? Okay, this is a pretty silent group. Yeah, so just deep diving a bit into EV two-wheelers, right? So this is not a full-fledged architecture, but it has the key components. So when it comes to I talked about the hardware layer. If you remember the first stack, the stack diagram that I showed you. So look at it from now left to right. So the hardware layer are, in this case, or the hardware components are battery pack, which is associated with the battery management system, and that's the electronic component associated with the battery pack. There's a motor, and the electronic component is called motor controller. And the peripherals, which includes horns, switches, headlights, tail lights, etc., are all called peripherals, and they are controlled or associated with an electronic component called body control module. So these electronic components collect the data from the battery, from the motor, from the peripherals, and send that data to a gateway, which converts that data into a readable format for a computing device, which is called which is in our case a dashboard, to understand. Because these are in the form of these follow CAN protocol, but once it comes to vehicle dashboard, it requires that data to be converted into a different protocol, and that's the function of the gateway. So once in the dashboard, which is, you can think of it as a mini computer, and hence it's a vehicle ECU. So it has a processor, it has a RAM, it has a flash memory, it has an OS, and so on. So for example, at Aether, we use Android open source platform. Many cars or other vehicles also use Linux alternatively. So think of it as a basic computing module, like on a tablet, which has a display. So within that, again, there is an application called hardware abstraction layer. So what this does is it now reads all the data that has come from the battery or the motor or even the peripherals. It tries to make some sense of the data, any processing that's required, and then it will do two things. First is it will show some relevant information on your display screen, which is called the HMI applications that you see here. So HMI is human machine interface. So think of it as, right now, in this case, in our context, as a touch screen display, right? So that so for example, when you're riding, you want to show some information like what is my current state of battery charge. Now, in order to show that, the system has to constantly be receiving some information about its current state of charge, and that's the data that BMS sends. And when BMS sends that data, this hardware abstraction layer tries to make sense of it, figures out that okay, this is the percentage that um, I have to deliver, and it delivers that data to HMI, which is the data that people or riders see on their screen, which says that the current charge in your scooter battery is say 36%. Similarly, while you're riding, you will receive, you also show what is the speed of the, or what speed you're currently riding at. That's called the odo reading, and that will take data from the motor controller, which is the rotations per minute, and based on what is the government defined formula for it, it will the hardware abstraction layer computes that okay, if this is the rotations per minute that I'm receiving from the motor controller, then this is the speed of the vehicle in say kilometers per hour, and that is computed and shown again on the screen. And similarly, whatever else today that we show on the screen, we show even if there is a maps application, there is yes, as I said, speed, there is acceleration, and so on, and there are a bunch of things that we show. If charge is if there is a nearby charging point, we show that on the screen. So all of these are the ones that are shown on the display. The second part of the hardware abstraction layer is while some relevant information is shown on the display, there are, as I said, we collect thousands of data parameters at a frequency of 100 hertz. Now, what do we do with all that data? We actually collect it. The hardware extraction layer collects it. It compresses that data and sends it to the cloud, or even directly to to a mobile phone. And that's the job of the connectivity gateway. It actually takes all that data, it batches it, and it sends it to the cloud. And from there on, multiple applications can be built. So for example, all the battery BMS data, when it's collected, gives the company the ability to remotely diagnose if there is some issue with any battery. For example, if there is any cell imbalance, even preemptively, or you can build a logic or an algorithm that can detect that there is some issue with the battery. If let's say there's some customer actually complains, and the service guy, instead of actually having to go and collect the vehicle from the customer's location, or the customer having to bring the vehicle to the service guy can actually just on his screen just look at, okay, for this vehicle, these seem to be the parameter BMS, all battery parameters seem to be okay, but there seems to be an issue on the motor. So this is the remote diagnostics capabilities, right? So a lot of these applications are today possible because we are able to collect a very minutest detail of every single peripheral or component of the vehicle and send it to the cloud. In fact, a lot of you must have heard this whole concept of digital twins, and this is how digital twins are made, which is how do you take the current state of every single component of, say, a vehicle, and represent that in numbers or data on a computer, on somebody else's computer, and that is what digital twin is, and this connectivity platform actually enables that. So I'll pause here again, and so just to see if there are any questions, comments. Hey, just a question. Am I audible? Are people listening? Is it relevant? I'm going to pause my presentation here just to make sure that I'm just not just speaking blindly.
So, ma'am.
Yes, Abhishek. Yeah.
Hello.
Yeah.
Ma'am, could you please explain more about process of hardware abstraction?
So when you say process, what it does?
Hardware abstraction.
Yeah, so I'm clarifying. You want to understand what the hardware abstraction does? Uh, not
Uh,
sure.
Hello, ma'am.
Yeah, Abhishek, can you hear me?
Yes,
Yeah, can you repeat your question?
ma'am. Could you please explain more about process of hardware abstraction?
Yeah, so hardware, as I said, all these components send data in the form of a CAN, which is actually, a hexadecimal format. Okay. So it will send data in the form of like 0 1 1 0 0 0 1 0, and there is a logic to read. Okay, the first three digits of this is represents. Say for example the state of the battery, the next three digits represents the temperature, and so on. So you all these individual components, be it peripherals or motors or battery pack, end of the day send data in the form of hexadecimal digits, and as I said, those are actually a long strings of zeros and ones. Now, when all of this hits a hardware abstraction layer, in this case, so it has multiple functionalities. So it has to first read and understand what those digits are, um, as in when it's receiving. And then it also has to perform some kind of supervisory control. So, for example, there will be an algorithm in this hardware abstraction layer, which says that if the temperature of BMS is, say, beyond a certain threshold, then you stop the vehicle for safety reasons. I'm giving a random example. So it will have some of these functionalities, some supervisory functionalities, which it will read all this information, all this data that's receiving in binary. It will process it to understand what that data means. It will do if there is any action that is to be taken. For example, if the action is to cut off the motor, if the action is to actually say turn on the headlights, etc., it will send that signal back and back to these control units. For example, if it is to turn on the indicator, it will send that signal back to body control module so that it turns on the indicator. Uh, the hardware abstraction layer also, as I said, computes some important information like state of charge, which is the battery percentage. It computes what is the speed of the vehicle and a bunch of other things in order to in order for that information to be shown or shared to the display. And finally, the hardware extraction layer has something called a CAN parser, which is the system or the service which actually just converts all this data that's received from each of these components, and packages it in such a way that it's understandable by, say, another system which is in the cloud, and sends that to the cloud. So think of the hardware abstraction as it's kind of a layer which separates the digital and the physical. So whatever were the physical modules, which is the battery, the motor, and the peripherals, it receives their data and it starts making sense of that data, and sends that relevant data to the relevant applications, which in the case of a two-wheeler is an HMI, which is basically the display screen, and as well as a cloud, which is connected to a mobile phone as well. I hope that explains.
yes, ma'am.
Anyone else has any question? Okay, I'll move on. Yeah, so I thought I would best explain this through a couple of examples, so that you know how eventually, like while we are talking about the tech, the stack, how each of these say units work together, exactly how it actually comes out as an output for an end user. So here is one example. Yeah, so I hope you saw that application, right? Which is basically somebody was trying to move the vehicle when it was parked, and you see that the owner receives a message on the mobile app that this a theft is detected, and simultaneously there is also this headlights like blinking, the tail lights blinking. So this is one such example of a connected vehicle. So how does that actually work in the framework that we just saw? So in this case, there is a sensor called an IMU sensor, which basically gives along a three-dimensional axis the position of the vehicle, like how much it's rotated, and also the momentum. So that indicates whether, for example, if somebody is trying to move the vehicle when it is in a parked state, you know that that vehicle has had some momentum, some movement along certain axis. Um, so that indicates that, or that data is collected, and this is where the hardware abstraction layer uses the CAN parser. It has something called a sensor fusion algorithm. So this is one of the applications that I was talking about, the hardware abstraction, right? So it's taken the data which is just showing along each of the axes, the XYZ axis, what is the position of the vehicle and how much has it relatively changed, which is the momentum. So it's just receiving that data, but the sensor fusion algorithm, which is in this block in the middle that you see, is the one now making sense that if I receive this data, does this mean that the vehicle has been moved or not? And if the answer is yes, that means that this is a theft or a tow case, and that becomes an output. So now, in case of an output, what it does? So first thing, it has to start blinking the headlights of the vehicle in a way like the hazard lights, so that, and if it is a thief who is trying to steal the vehicle, is gets alarmed because the vehicle suddenly seems to have woken up. So what it does is that output is sent back to the gateway, and the gateway sends that back to the body control module, and it tells the tail lights in this case to, let's say, start blinking. That happens. There you can also define a timer and say that, okay, blink for 2 minutes, 3 minutes, and so on. The second thing that it does is simultaneously, since it has now detected that this vehicle has been is in a state of theft or tow, it sends that information over to the cloud, and that cloud on the cloud actually processes that information and sends it to the mobile app of the owner to say, it looks like, hey, looks like your vehicle seems to be either in the state of theft or tow. If required, just like take action. That's how this whole connected stack comes together for building an application like a theft and tow detection. Any questions from anyone?
Yes, ma'am.
Yeah, go ahead.
Ma'am, this IMU sensor, is that inertial measurement unit?
Correct. Yes, it is.
So is there a difference between IMU and INS, inertial navigation system?
I am not sure about the which is the other one that you mentioned. Induction.
The inertial navigation system.
Okay, I'm not sure about it. That I
Okay,
don't. That's not something we use. So we use IMU sensor. So I'm more familiar with it.
Okay, ma'am. Thank you.
Any other question from anyone else? Okay. So here is another example. All right. So what you just saw was now Bluetooth-based call control. So I actually forgot to mention one thing in the previous example, right? So when the owner receives a theft alert, or when I talked about in general the whole sending the data over to the cloud, that data is being sent through 4G. But this is an example where you're not using any of the cellular technology. You're actually using Bluetooth. So in this case, what happens is think of it the 450 as another smart device. Okay, 450 is our vehicle model. So think of a connected vehicle as a smart device, right? So it is paired with your phone like any other like how your headphones are paired with your phone. And there are these concepts called in Bluetooth called profiles. So if it is in case of an Apple or basically an iOS, the profiles are notification center, I think messaging services, and so on. Similarly, in case of Android, the profiles and these profiles can also be created like as part of your code, like writing the code. So what a profile means is that you are defining what kind of data you're going to exchange via Bluetooth channel. So it could be call information, as you can see in this case. It's call information service, it's music information, and it's also pairing service. So these three channels have been created between the vehicle and the phone. And this is just an example. By the way, you can extend this to also include other things, for example, SMS service, WhatsApp service, as long as those services have APIs that you can actually create a channel for that data to be exchanged between devices. You can create those channels, and that's how you integrate more and more applications. But in this case, since this feature talks about controlling call or music from your vehicle, what happens is first you create these services that are exchanged between the phone and the vehicle. Now, one unique thing here is that since there are no mic or speakers, say so to say, on the vehicle on a two-wheeler vehicle, um, then you can only do any stalking. For example, if you choose to accept a call, if you have to talk, you cannot yell into the dashboard, yell into the scooter, because the scooter does not have mics, which means that you have to use a Bluetooth headset. So if you have a Bluetooth and you're on, then that is also communicating with the phone. So the vehicle on its dashboard has received some information. While you're riding, you're receiving a phone, and your phone is in your say either your bag or your pocket, and a call has come. Now, while riding, it's very difficult to say pick up your phone. So what happens is that information is sent to the scooter, which is a touchscreen display. Now, while riding, none of the touch functionalities work. That's a safety-based design. So the only thing that you can control while you're riding is through switches. So you accept or reject the call through a switch. So as you saw in that ad or in the video, that it sees that it's a spam call, and that rider actually just rejects it by turning the one of the switches to the left. You can also accept it, in which case, let's say you turn that switch to the right. So once you accept it, what's happening is the vehicle is now communicating to the phone that, hey, this call is on, and so the phone actually accepts that call. And phone is also, since it's connected to the headset. Now, when you're speaking on the headset, it's pretty on your, say, Bluetooth earphones. That's pretty much like speaking with your any of your earphones on while a call is going on. So all that in this case that the vehicle is doing is that because while riding, it's very hard for you to see what's happening on the phone, and it may be some urgent call that you have to receive. Maybe your parents are calling, worried that are you going to be home or not, and you just want to assure them without necessarily, say, finding a place to stop on the side or so on. You can just quickly accept the call, say that, hey, I'm on my way, and be done with that call. The vehicle in this case is through vehicle, you're just controlling now phone functionality. like what you would have required for, to actually pick up the phone and say press that accept button. You can automatically do that through vehicle by sending that command from the vehicle to the phone, that accept. No. Similarly, you can do that for music as well. And as I said, other applications like messages, SMS messages, WhatsApp messages, and so on. Any questions here? All right. So, yeah. So, as I said, for me, I mean, primarily those were some examples, a very high level view of how to look at the whole connected stack. Coming to overall, how can you now, I'm sure a lot of you must be wondering, okay, how can you actually participate if this is an area that excites you? So definitely work on, keep tinkering with things in your college projects. As I said, while it's saying connected vehicle, it's this whole technology is similar for any smart device or any IoT application, which also includes drones, by the way, if any of you are excited about that space. So overall, what I would really encourage you guys is to build working prototypes. If you participate in robotics competitions, you'll again get a lot of sense of, because same thing in case of a robot also, what's happening is you have a physical device that's connected to a set of electronics, and remotely you're trying to control, or you are building some intelligence within the robot to what we call as the parse the data and control the actions of the robot. Definitely be a part of college formula teams. I've seen a lot of people from engineering colleges who are able to join at least Aether, and I'm sure that's the case with many other automotive companies as well, are actually have participated in formula teams. So they get some kind of knowledge and hence an interest in terms of what kind of problems you get to solve. Finally, yes, look for an internship. Again, there are different places. If it's OEMs, which is actually big automotive companies, there are startups like Aether, Ola, etc. There are also big companies like TVS, Bajaj. So you can apply for internships in these companies. You can also work with component suppliers, which is actually also a pretty large space. For example, there are a lot of startups which have come up in the space of battery management system, battery packing and management system, or motor, and they sell these motors to actually these OEMs. So example would be Bosch, Euler Motors, Harman, Samsung, and by the way, these are all fantastic companies to work at. If charging infrastructure excites you, that's another application of say connected tech. So in this case, the device is a charging unit, which is made smart by, again, say the whole connectivity platform. So charging infra startups are the places. You can also go into adjacent industries, as I'm constantly reminding, or emphasizing this group, that end of the day, connected vehicle is just a domain specialization within the broader IoT, which means that drones, wearables, industrial IoT are all great places to be at. Yeah. So in terms of what kind of, in that case, the jobs, and hence how does that relate to your specific branches that you have chosen. So there will be electrical and electronics architecture. For example, this high-level block diagrams that you saw me putting together, a very, very detailed level of that is actually what is called E&E architecture, and that requires backgrounds in electrical and electronics engineering. The hardware design of a dashboard, which is basically almost like a CPU design, but now specific to an automotive use case. And if you are going to say a space tech, it would be specific to a space tech use case. If you're going to a drone company, it's specific to a drone use case. So the design of what is ideal chip design is something that you would get to do in this space. And obviously, a good background there would be in electronics engineering. Systems and controls are what we at Aether call system intelligence. That's the team which builds algorithms, or what we call as smart algorithms. For example, while the IMU sends data that this is the XYZ coordinates or this is the angular rotation or momentum, um, there has to be an algorithm which is actually constantly figuring out that the data I just received, does it mean the vehicle is fine, or does it mean that it's in the state of, or if somebody's trying to steal it. That is an application of system, like that's an algorithm called system intelligence. So that again, electronics engineering, I would say it also takes people from other branches. Firmware development, obviously embedded systems. So um, a lot of mission critical functionalities may be more localized. For example, in case there is a very battery critical functionality that you want the battery to control, like if for example if you're seeing the temperature increase beyond a certain point and you want some action to happen, you may not want to wait all the way for the battery to send the data over to the hardware abstraction system, which is computing and sending it back, because that takes time. Any processing takes time. So maybe there are certain algorithms or functionalities that you want to develop that is just localized to a BMS, and all that would be part of obviously firmware development. AOSP in this case, again, this is, as I said, it's basically an OS, which is Android open source platform. And as I said, alternatively, Linux is also something that people develop. So that's one area or one branch within software engineering that people can pursue. If you're more interested in, say, big data, when I say cloud, honestly, what I'm referring to is distributed systems and big data. That is definitely a must in order for you to be a good backend engineer, which is basically what I'm referring to constantly as cloud. If you're excited about front end, then mobile app development is what you can pursue. And finally, data science and machine learning. I think in this age or era of generative AI, there's still a lot of exciting machine learning algorithms that you can build. So all this, hundreds of gigabytes, or like I think now many companies must have, achieved even like petabytes of data stored that is collected from the vehicles. How can you build more intelligence on, say, predictive diagnosis, etc., is actually an application of machine learning and data science. And that's, if that's an area that excites you, that would be an opportunity. So yeah, I think I am done. So thank you all. I'm open for any questions.
Ma'am,
Yes, Abhishek. Yeah.
what can I do to get the internship in connected vehicle sector?
So, I mean, usually when it comes to campuses, campuses have relationship with companies. If your campus has relationship with companies that I listed in as examples, that would be and you have a formal internship program, that would be one way. If you don't have that, my suggestion is get onto LinkedIn. Find out in each of the research about these companies, the companies which are operating in say EVs, or even big companies like say TVS, Bajaj, or in the component space, as I said, right, Euler Motors, Log9, etc., are all great in say battery motor manufacturing. So you can actually find out maybe who in your specific area is actually there. You can find out by typing in the rules like Euler Motor, say system engineer, and you will get a few names. Reach out to them, share your CV, and hopefully in your CV you have some exciting projects that you have done to talk about, which demonstrates the interest you have, and request for an internship. As I said, if you do not have a formal program via campus, be very persistent, and put yourself out there. Try and reach out to the people, showcase why they should say give you a chance for internship, which means that you should have invested time in your college building projects that are that demonstrate that you can actually contribute during your internship. Yeah, I would say that's how you will reach out.
Okay, ma'am. Thank you.
Hello, ma'am.
Hi, Varsha. Yes.
My question is that how do you envision the evolution of this urban infrastructure to accommodate the increasing integration of connected vehicles in our cities?
So that's an interesting question. I'm glad you asked that. One of the things, at least what we foresee now, is actually this as we see the evolution of smart cities, smart roads, smart traffic lights, etc. It actually gives us the opportunity for the vehicles to connect to these and hence become strong, say much smarter. For example, the traffic can get more, the traffic light algorithm can get more intelligent if it knows real time which vehicles are actually waiting there, as an example. But honestly, I think that level of, say, urban infrastructure getting fully smart is quite a while away. By quite a while, I mean at least half a decade away. But what is definitely getting there today is, for example, smart parking systems. There are a couple of startups. If you're interested, you can look them up. One of them is called Park Plus. I'm not able to think about anyone else. But yes, Park Plus is one such startup which has these parking spaces that are smart, and so it knows in real time that if there are vehicles which have parked, and hence when the vehicle is connected to these to say a Park Plus system, the vehicle knows that what are which is the nearest parking place where I have a slot to park. Similarly, if you look at one of the other interesting applications, and that's something has been recently launched, I think by definitely Mercedes, I don't know BMW, maybe BMW as well. And something that we are also evaluating is connected with, say, the health response systems. Now, honestly, the way the government ambulances are, they are still not at a place, or they do not have the tech directly that they connect, uh, say, like, for example, you can connect your vehicle to any of these emergency response platforms. But if there is an intermediary, which is another startup which has created some kind of a platform which on one hand connects with the vehicles, and on the other hand, say, connects with the ambulances. The application is that if there is an accident detected, which again is so, for example, we can detect if a fall has happened in ether today. So let's say somebody has fallen, and we can detect its severity as well. It can automatically send a call to an emergency response platform who can coordinate with, say, any of these health providers, be it hospitals or ambulances, to go to the location of the scooter. And because it's connected, the scooter can also send the location to them. So this is how I see, at least with some of the public urban infrastructure, some applications evolving today, but the larger ones of smart cities, roads getting smarter, traffic lights getting smarter, for example, that I see still, say, about half a decade away.
Thank you, ma'am.
Anyone else? All right, so we call it a day. Cool. All right. So thank you, everyone, for listening to this session. I hope it got you excited about this space. I'm sure some of you are probably already working on some projects in this. Keep an eye. There are tons of good articles on this that will take you much deeper into what I have at least been able to cover today, and a lot of projects that you must be doing. You can. You can see if there are certain applications that you want to develop as part of your projects.
Thank you, ma'am. That was a wonderful section. I extend heartful gratitude to all participants and speakers for making our online session on connected vehicles a resounding success. Your insightful contributions illuminated the intricacies of this transformative technology. Special thanks to our esteemed speaker who shared their expertise providing invaluable perspectives. The engaging discussions and thoughtful questions showcase the collective commitment to understanding and advancing in the realm of connected vehicles. I appreciate the organizer for orchestrating the enriching event seamlessly. As we embrace the future of transportation, let's carry forward the knowledge gained today to contribute meaningfully to the evolution of connected vehicles. Thank you for your active involvement, and I look forward to continued collaboration in exploring the boundless possibilities this technological frontier offers. Now I invite Madhavesh Nair, former chairman of IEEE VTS SBC NSSC, to hand over the virtual memo.
It was a wonderful session, ma'am. Thank you from the bottom of our hearts.
You're welcome. And thank you for all of you for attending the session on a Saturday evening, that too. One day before the World Cup, so I understand the. Yeah, please go ahead. Sorry, Madhav, you raised your hand?
Yeah, ma'am. That was by mistake, sorry.
Okay, yeah.
Okay, now, participants, please turn on your cameras. We can have a small photo session. Okay, thank you all. Thank you, ma'am, once again.
Thank you. All right. Thanks, guys. Bye.
Now everyone can leave the session. Thank you for your participation.